All right. What perfectly timed webinar today, guys, with all
Indeed.
these storms going on and everything. So thank you all so much for being here this morning. My name is Chelsea Broad-Merkel. I'm marketing director with Kipcon. If you need your CEU credits or you have any questions at the end, I'll put my email in the chat at the very end. Usually I'm not sharing my screen, so it's a little more difficult to do that. So I'll put that at the end for everyone. But you should have gotten some kind of email me from me in the past or from our info mailbox. So feel free to shoot email to myself, info, or John Stevens. Email is down below here. But thank you all for being here. John Stevens has been with Kipcon for, I don't even know, John, has it 20, 30, 40
Com-
years?
Coming up on 40 years.
So he knows what he's talking about. So I'm going to let him take over and give you guys some good tips on all these winter storms going on.
Okay. I have one more problem.
What's the
Wait.
problem?
Um, I seem to not be able to manipulate the PowerPoint.
That's me. I'm going to control it. Just let me know what to do.
Okay. All right. Okay. So this is a pretty appropriate talk I'm gonna give today about winter conditions and in particular ice damming. Um, Given the snow over the weekend up there. I have to tell you, I'm not broad doing this from New Jersey. I'm in South Carolina. Um,
Bragging.
no, it's really it's in the temperature is in the low 20s here today, so we're not much different than Jersey, except we have no snow. Um, but given the weather up there with snow over the weekend and now very cold temperatures, those are prime conditions for ice dams to develop on buildings. The and I'll get into that and why that happens. But yeah, that as long as there's snow blanketing the roof, there's a very good chance ice dams are going to form. So we're going to talk today. Going to go into roofing, roofs of buildings, the parts of roofs, how they all work and how they fit together. And then we'll get into some of the winter issues like particularly ice damming. And we'll go through that. And some point there'll be a CEU keyword given. And then I'll talk about the causes, signs, symptoms of ice dams, and some potential solutions. So, so anyhow, parts of the roof. We're going to concentrate mostly on shingle roofs because those are the type of roof most vulnerable to ice dams and leaking as a result. Um, and the reason for that is the sloped roofs that are usually have shingles on them at the edge of the roof or the eave. There's generally gutters um, and downspouts to direct the water runoff from the roof shingles, in a controlled manner down to the ground. And it's the nature of the edge of the roof at the eave that is where the problems result from ice damming. But just to run through that diagram on the screen, um, the areas where things project from the roof. The dormer, which is on the right side there, you'll see there's a valley on either side of it, and that's where two roof planes intersect, and that's an area that can be vulnerable to ice buildup and leaking as a result. Um, you'll see there's a chimney up on top of the roof at the ridge, and that would, again, because it comes through the roof plane, it's an opening that's flashed and but has the potential to have leakage around that flashing or sealing. Same thing going further to the left in the diagram, you'll see a sidewall where the roof changes elevation, where that lower roof plane butts up against the sidewall. That's also a vulnerable area. Um, and so, I'll get into those things, but Those are the things. And again, there's a dormer at the lower left of there. Flat roofs, when they're in the context of this diagram, they also can be vulnerable. But if you have a building that's completely covered with a low slope or flat roof, the drainage of the roof is completely different than in a shingled or pitched roof, and so much less vulnerable to having ice dams form. Um, okay, so we're gonna concentrate on shingled roofs. Um, Shingled roofs are not waterproof. They're weather resistant, and they rely on gravity to drain rainwater or snow melt from them. And as I said previously, the generally that drains into a gutter and downspout system at the eaves. Um, in most situations, this works very well. The shingles are overlapped. The water runs down through gravity, gets into the gutter, drains down through the downspout to grade or underground into a drainage system. Um, so the problem you have is when the edges of the shingles are not they're not watertight. So if you end up with water backing up the roof for some reason, you can get leakage through there. Okay. So as I talked about, the photo you see here is a sidewall situation. So that lower roof is intersecting a vertical wall. And in order to keep water from penetrating at the base of that wall, you have to use flashing, which is shown in the lower diagram or the lower photo. And flashing is typically aluminum or copper or some other metal, thin pieces that are basically at 90 degrees, so it's sort of an L shape. One leg of the flashing goes under the shingles and the other one goes up the sidewall, which you can see in this photo. The flashing also overlaps just similarly to the way the shingles do. And again, it keeps water from penetrating at that intersection of the sloped roof and the sidewall. One of the issues, though, and that works fine for general conditions where it's raining, but when you get snow on a roof, you can see that the flashing pieces are not, they don't go up the wall very high. They're generally 5 to 7 inches high. So if you get snow that accumulates higher than that on the roof, it can actually, when it melts, it can get behind the flashing pieces. Now, you try to mitigate that by when you put the underlayment of the wall, which these days is typically Tyvek or some material like Tyvek, you lap that properly so that water that gets or snow that's above the actual metal flashing doesn't penetrate behind it. It hits the Tyvek and then runs down and where the metal is and then down the slope of the roof. You'll notice at the bottom of that that line of flashing is a piece of white metal flashing, and that is called a kick-out flashing. That's used where the roof ends before the wall, the vertical wall ends. And you can see in that picture, um, the wall is there even past the end of the roof. That kick-out flashing is put there with the intent to divert any water running down the roof from snow melt or rain, to keep it from going over the edge of the roof and running down the vertical wall. It diverts it into the gutter, which you can see in the bottom part of the photo.
And we have a
All,
question.
yeah,
How does flashing against brick work?
okay. When you're flashing against brick material, the way you need to do that is you need to, it's called to let the flashing into the brick. So the flashing, in the case of what we're looking at here, the flashing is a simple, um, it's an L bend. It's a 90-degree bent piece of metal. If there was brick on that wall, the top part of that flashing would be bent back towards the wall at 90 degrees, and then it would run down. If you can envision the joints in a wall of brick, um, it would follow the joint line down. The joint would be cut, or when it's first installed, it would need to be cut. You'd actually let the other leg of that flashing into the brick joint, and then mortar around that, and then that would form a solid shield for water coming down the roof. It's a little more complicated than if in the photo I have here on the upper one is a vinyl siding or maybe cement board siding or something like that. That's a much simpler way. The way you flash that is a much simpler way than with brick, but that's typically the way you would do brick is to actually turn the flashing into the brick joint and then seal that up. Um, you do see brick flashing where it's only on the surface of the brick, and then it's sealed with caulking or some other sealant, flexible sealant material. That that'll work. It's all, however, it is you got to keep sealing it. It's vulnerable to the caulking or flexible sealant deteriorating because of the weather, because it's exposed. So it's not really the recommended way to do it, although you do see that on projects.
Perfect. Right.
Okay. So this is two diagrams show you why flashing matters at a sidewall. Um, if you in the one on the left, which is the good diagram, you'll see that there's house wrap, there's counter flashing, there's the sidewall flashing, and they all overlap similarly to the way shingles overlap, where the water coming down the vertical wall would shed off the house wrap, off the counter flashing, off the sidewall flashing, and then down onto the roof and be, you know, drained away into the gutter. Uh, on the right, you can see that the house wrap or the Tyvek is actually put behind the counter flashing. So any water that gets inside the siding and runs down the house wrap will run behind the flashing and then penetrate into the building. So it's not only having flashing, but installing the system correctly is very important to keep water out of your building. All right, as I said earlier, there's different kinds of flashing, different materials. Flashing that's exposed is generally made of metal, uh, zinc-coated aluminum, copper. Copper is not used very much anymore because it's very expensive, but these other types of materials are used. One thing to just consider with flashing, uh, aluminum flashing cannot be in contact with masonry. Um, it'll deteriorate the aluminum. So if you're putting flashing on a brick installation or stone or stucco, it has to be zinc coated or galvanized flashing that will not deteriorate because of the exposure to the masonry material. Um, and then there's also membrane type flashings in a lot of areas where the flashing is concealed behind siding or not exposed to UV particularly. You'll see self-adhered membrane type flashing that's used. It's got a adhesive on the back of it, so it sticks to the wall, and it's somewhat flexible. So if you have situation where you need uh, to be able to withstand some expansion and contraction, you can use these membrane type materials. The one thing about those is though they cannot be in an exposed situation because UV, sunlight, ultraviolet radiation breaks down the membranes and they'll decay pretty quickly.
Another question.
Yeah,
If the,
I see. Yeah, I
you
see
see
the
it?
question.
Okay.
No, you can use membrane type flashings in retrofits or if you're redoing a roof or whatever. Um, they as an example, if you were putting this has nothing to do with ice damming in w winter, but if you're putting windows in a building, replacement windows, you can use flexible flashing around the flanges of, the jambs and the head and the sills of the windows. Um, so yeah, it can be used in either. All right. So as I said earlier, most roofs, pitched shingled roofs, drain the water that runs down them through a system of gutters and downspouts. The gutters are installed along the eaves. They're pitched to drain to the various downspouts that would be installed on the building. Um, and the downspouts then would drain water to grade, or sometimes they're actually put into a piping in underground and run directly into the storm drainage system. The sizing of the gutters and downspouts is based on the building code and is set by standardized calculations of local rainfall for your particular geographic area, and also the size or the area of the roof section being drained. Um, Now, that the kind of odd part of the building code is it does not specify the length of the gutter or the volume of the gutter, only the size, the diameter, or the cross-section area of it. So if, for example, you have a large section of roof draining to a 2 or 3 foot long gutter, that's probably not going to be adequate, even though the gutter's size might be big enough. Um, so uh, there's some oddities in the code that doesn't really account for how much volume of water a particular piece of gutter can carry, and sometimes you see issues as a result of that. Generally speaking, the question is it's 1 inch per 10 feet as the slope that's shown in the diagram. Or, I'm sorry, 1/4 inch per 10 foot. Um, so but this is generally what's done, and it comes into play when ice dams form on the roof, and I'll get into that a little bit further into the presentation. Okay, the other area that's critical in formation or lack of formation of ice dams is in the attic. Um, Building attics, obviously, is the area above the top floor ceiling, below the roof. You can see in this photo. Um, the attic is an unconditioned space in the building. It's not heated or cooled, but it does play a major role in controlling the temperature in the house or building by being properly ventilated, um, and properly insulated. Um, Attics are also can be used for storage if the framing design is such that it allows storage. Just as an aside, today, since most um, residential buildings are using roof trusses, um, the they are not typically designed for allowing storage in them. So, yeah, if we can go to the next slide, please. So typically attics are insulated. Um, and again, for the most part, you'll see fiberglass bat insulation today. There's other types of insulation. You have spray insulation, spray foam, blown in loose insulation, but the most common insulation you see is this fiberglass bat type insulation that you see in this photo. Um, Obviously, the purpose of insulating is to prevent heat loss from the interior spaces, help keep the living area below the attic comfortable, help lower your heating bills and cooling bills in the summer, and try to keep the warm air or cool air that you're producing inside the unit rather than into the attic and escaping. Now, insulation is kind of key to ice damming, and I'll talk about that a little bit, and what the difference is between older buildings that are not heavily insulated and newer buildings that are. Also, in this photo, you can see the pink uh, pieces of material that are kind of running up the slope, underneath the slope of the roof sheathing. Those are ventilation baffles, and those are put in there to allow the airflow from the soffit to get up into the attic space and help ventilate the attic. Um, Typically, the insulation um, is not held back from the soffit areas. It's pushed right out till it touches the roof sheathing. And without those baffles, then all the ventilation would be cut off by the insulation. So um, again, in typical construction that we see, those are those are a key thing to look for in an attic because they ensure that the ventilation will occur as it's supposed to be. Here's a diagram about ventilation. So you need to have a proper ventilated attic, you need intake and exhaust. So typically the intake is using vents in the soffits, which are the underside of the roof overhang. And you can see in this diagram, that's at the bottom left, and there's vents in there, and it allows outside air, fresh air to enter the attic space. Um, in this diagram, the insulation is held back from the soffit, so there's clear path for the air. In the previous picture, the baffles were performing the same function of leaving space for the air to flow. So generally speaking, air comes in at the lower part of the roof and vents out at the upper part. That can be through ridge vents, which are installed along the ridge or the top of the roof. It can be through vents installed in the surface of the roof that are, they're generally square, low vents. Those are passive air vents. Or you can power vent using fans. Um, but those are the ways typically that the upper part of the roof is ventilated. And the building code uh, typically requires a certain amount of minimum ventilation in an attic, and it's calculated based on uh, various factors, vapor barriers in the attic space, and so on and so forth. I won't get into the actual calculation, but it requires a certain percentage of the airflow to come from the lower vents and a certain percentage to come from the upper vents. And that would determine the sizing and spacing of the various vents in the lower and upper portion of the roof. Um, so it's okay. There's a question about condensation in the attic. And basically, condensation is more prevalent in the winter because of the uh, typically large difference in outside air and inside air, attic space air. And it's due to the fact that the attic's not ventilated properly. And so by allowing the warm air, it also can be caused by a lack of insulation, adequate insulation. Warm air gets into the attic space from the conditioned space below it, the living space, and the, the cold air on the outside, when it hits the surface of the sheathing or other components of the attic space, then moisture condenses out of it. And if you see condensation, one of the evidence of condensation is if you look at the shingles, the nails from the shingles that penetrate through the roof sheathing, if they're all rusted on the inside, that is a good indication you're getting condensation in the attic because they're not exposed, so they shouldn't be rusting due to any other, from rain or anything like that. Um, so yeah, it's probably a combination of poor insulation and poor ventilation. Cathedral ceilings are similar to other type of attic space, where you have room. Um, much more critical there though for ventilation because you don't have all the space you have in uh, a non-cathedral ceiling attic. Um, so as you can see in this diagram, there's very little space between the top of the insulation and the actual roof deck, and between the warmer air coming up from the uh, living space and the cold air outside on the exterior. So ventilation is really critical here and making sure that it's open all the way up. Because you can see in the diagram that the insulation, the small space for airflow runs all the way to the ridge in here, whereas in the previous example, where you have what I'll call a regular attic, um, you only got to get the air from the soffits up into that large space, and then it flows without any problem. So a little more critical here to make sure everything is ventilated and insulated properly. All right, so just to recap, I guess, this is all a system. The roofing, the shingles and flashing keep water out. The insulation keeps the house warm and cool. Ventilation keeps the attic proper airflow, and as I said previously, keeps moisture out of the attic, or condensation basically out of the attic. If you look in this diagram, though, oh, sorry, the one thing I didn't at the top, you can see there's those two lines. That's a ridge vent there. That's showing you the actual vent, and then the vents are capped with shingles, which is the top dark line in that diagram. And also, as you go down under the shingles, you'll see pink and white. And that's the roofing underlayment, various types of materials. Older buildings will just have roofing felt, which is basically heavy paper impregnated with tar to keep the moisture out. There's more, recent materials that are more like house wrap or Tyvek that are commonly used now. But down at the very bottom, you'll see a wide dark strip. That's a membrane underlayment that's installed at the edge of the roof or the eaves of the roof. It's commonly called ice and water shield, even though that's a brand name. But that, it's sort of like calling all Coke or all cola soda Coke. But it's ice and it's typically a self-sticking membrane that when you put the shingle nails through it, they seal around it. And that helps to prevent when ice dams form, the water from backing up under the shingles and into the house. And I'll get into that in a little more detail, but I just wanted to point that out in this diagram. Uh, I didn't catch that question. Chelsea, you have that one?
Yeah.
Something about,
Yeah. Is there a vapor barrier in the roof slash ceiling assembly?
yeah, typically, well, the underlayment of the roofing is an exterior vapor barrier, but in the attic, most the fiberglass bat insulation on the underside of it has uh, a plastic or paper vapor barrier that uh, is in the attic space. If you're using blown-in insulation, you got to make sure you have a vapor barrier before you blow the insulation in. But the fiberglass bat stuff comes with a vapor barrier attached to it. Um, okay. All right. So on the left, in the wintertime, now we're getting into the conditions where ice dams occur. Um, you have what's called a functional attic. It's got heavy insulation. You see that's an R50 insulation, which is a lot of ceiling insulation. It's got open venting, so you get a lot of good airflow up through the attic and out at the ridge. And one of the things that I haven't mentioned, but I will here, you'll see it talks about making sure that penetrations through the ceiling, vents, recessed lights in the ceiling are properly sealed to minimize how much heat loss you get through those things. If you don't have that, you get a tremendous amount of heat loss uh, through through those penetrations into the attic space, which then warms up the attic, which I'll get into why that's a problem with regard to ice dams. And you can see over on the right-hand side a dysfunctional attic. Um, you got block vents, you got minimal insulation, and then you're getting ice dams building up on the outside and condensation on the inside. So that kind of shows you the results of not having proper attic construction. Okay. All right. One of the things you got to remember about ice dams is they're caused by Mother Nature. You can have a perfectly constructed roof, and if you get ice dams on it, you can get water leakage into the interior spaces. And it's not a defective roof construction. It's just the result of weather conditions. Now, having said that, improperly constructed roofs will aggravate the situation, uh, more than, you would normally have if the roof was constructed properly. So proper construction is really important, uh, but it can't prevent the formation of ice dams and potentially leakage from that. So here is a very classic look at uh, ice dams that are formed at the edge of this roof. A couple things in this photo that would, aggravate the condition is these confined areas, like between the large dormer and the small dormer. That small little area in there is prone to accumulation of snow and then eventually ice. And you can see this roof has several of those small areas, and they're all full of ice at the eave. Um, so, ice dam, if you don't know what it is, it's a dam or a ridge of ice that forms at the edge of the roof and prevents um, snow. So it forms at the edge of the roof, and you can see in this photo that there's snow still on the roof above those areas. As that snow continues to melt on the roof, uh, it will not be able to drain because of those ice dams. And then what can happen is the water, that liquid water backs up under the shingles and then can leak inside. The question is roof heating coils. And I'll talk about that later. There's pros and cons to those, which I'll get into in a little while. Um, so, as I said, first thing, you got perfect conditions right now in New Jersey and a lot of the northeast uh, to form ice dams. You have a blanket of snow on the roof and below freezing temperatures. And even if the temperature gets somewhat above freezing in the daytime, once it goes below freezing after sunset, um, it, you can have ice dams form. Um, this photo is a good example of the third bullet point, aggravated by the particular construction or design of this building. And again, as I said a little bit ago, it's caused by Mother Nature. All right, so this is how ice dams form. You can you get an indoor heat loss. You're heating up the living space. Some of that heat escapes into the attic. And depending on your attic construction, that can be more or less if properly insulated, not properly insulated, and that type of thing. But even with insulation that's proper, ventilation that's proper, you're going to get heat loss up through the ceiling. And what happens there is the warmer air rises up to the upper part of the roof. And particularly if you don't have proper ventilation, it warms up the underside of the roof sheathing and therefore up through that into the underside of the shingles. So what you get is up at the ridge, you get melting of the snow. Even if the blanket of snow is covering it, where the bottom of the snow meets the shingles, you'll have melt water in there. And that water runs down the roof. However, when it gets down to the eaves where there's much less insulation, um, it gets cold and it freezes. It refreezes down there at the bottom, um, just because of the nature of the way a roof, the geometry of a roof. Down at the eave there, where you see the number three, um, the air is cold down there, and if the outside air is below 32, that water refreezes there. And it's a gradual process, but if the conditions persist, you'll get ice build up, a little bit at a time until you have a ice dam that blocks any further flow of water off the roof. And then that's where you end up um, with a problem because the meltwater now has nowhere to go and it tends to back up and by doing that it gets under the shingles and then into the living space. So in that earlier diagram where I talked about ice and water shield, that's one of the reasons why ice and water shield uh, is 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 put in and in. I didn't mention that earlier. Um, in a lot of areas, it's actually required by code to be installed. Um, so, uh, but it's also typically installed today and when roofs are put in. So the ice and water shield typically comes in 3 foot wide rolls, and there is a calculation that the code requires uh, to see how much ice and water shield you need. I don't remember it off the top of my head, but it has to extend so many feet inside the the horizontal or the vertical exterior wall. And then when you put that up on the slope of the roof, you have to do that calculation to determine how much width of ice and water shield you need. Now, the intent of that is to prevent that dammed water in where red number two is there, to prevent that from leaking into the living space, because that forms a solid membrane. So even if the water gets under the shingles, it can't get into the interior. Um, it doesn't prevent ice damming. The ice dams still occur. You just prevent the damage as a result of ice dams. Um, okay. And here's some, and the answer for this question, ice dams happen even if perfectly insulated. Yes. And there, and I'll talk a little bit about this going forward, but there are really extraordinary ways you can construct a roof that would absolutely prevent ice dams. But, you know, almost universally, they can still form if the conditions are right, regardless of whether you have proper insulation, proper ventilation. Um, it's a weather phenomenon. Um, so anyhow, these photos show some of the damage that can result. The one on the upper left is actually soffit damage, which although is, that's a problem. It's on the outside of the building, so there's no, damage to somebody's living space in this photo. And you can see in the soffit, you see all that white material is ice. Um, and that's how much ice had built up in that soffit. Um, the next one, going clockwise, you see the gutters damaged by the amount of ice that's in it. That's real typical. And you can see when you look at the roof above where the gutter is bent down, all along there, that's ice up there, along with snow. That darker grayish, that's basically ice, and that's an ice dam. And they can still occur even with the gutters, with no gutters on the roof. If you go to, up into New England and, the upper Midwest and places like that where they get a lot of snow and it's every winter and they experience these conditions, most of the buildings do not have gutters on them. But ice dams can still occur, and I'll get into some other ways to keep that from happening. But even without gutters, you can still get ice dams. They exacerbate the issues, but because I've had clients where they went around and removed all the gutters from the buildings, thinking that would, then get rid of the ice dams, but that they just formed further up the roof. That's all. And then you can see moving down to the next photo, there's water damage to the ceiling. Now this is inside, obviously inside a living space. And then the last one there is you can see the sheathing's wet, and that's the roof deck there that you're looking at from the inside of the attic. So yeah, that's the kind of damage you can get. Now, here's what I talked about earlier about old buildings and newer buildings. Um, the little diagram on the left, it just snowed and the storm ended, and that's what the roof looks like. If you have an old house um, where they're not very well insulated, you get a huge amount of heat loss. And old houses weren't insulated mainly because um, the cost of energy was really, really cheap. And so it really didn't matter that you blew a lot of your heat out through through the roof. So what happens there is you can see that most of the snow is melted off the roof, and the only snow that's left is down at the eaves. And you can still get ice dams, but the fuel for water penetration as a result isn't there because there's no continuous snow melt coming from the upper part of the roof. the snow's gone. So uh, you might get some minor conditions with the result, but generally there's not an issue there. However, um, you don't see too many houses like that anymore because it's been 40 or 50 years of concern about energy use and heat loss that have factored into building construction. So, vast majority of homes and buildings you're going to see today are the third diagram, which is modern roof. You're losing just enough heat to cause the snow melt, which results in the ice dams and the potential water penetration. Um, and that's pretty typical for modern homes. Now, somebody asked a question about preventing ice dams if proper insulation. That diagram on the right there is called a cold roof. And there's several ways to do it, but the most typical is to basically build a double roof. So you build an inside roof with sheathing, and then you, on top of that, a foot or two, you put the outside roof, which has the shingles on it. And what that does is the the heat loss is absorbed by the inner roof, and that space between the two roof decks is generally the same temperature as the outside air, and therefore the snow doesn't really melt like it does in either the modern roof or the heat waster roof. And so you see that the blanket of snow stays relatively intact, a little bit disappears along the edges, but the roof stays pretty much solidly covered, and therefore you're not getting the melt and the refreezing at the eaves and the continual melt water backing up into the living space. Nobody builds roofs like that, though. So you'll probably never see one of those. But that is a way to prevent ice dams from occurring. All right, so here's our keyword. It's called sublimation, which is, as the definition implies, it's when solid state, which is snow in our case, goes directly into a gas state without becoming liquid first. Um, and you'll get that when the air temperature is below freezing, um, and the snow actually isn't melting, but you'll see it disappear. You see that, excuse me, you see that a lot um, at um, in the mountains at higher elevations where the snow tends to sublimate and not go from solid to liquid and then to gas through evaporation. Anyhow, we'll move on from that.
Yes, and just a reminder to everybody, I put my email address and our info mailbox into the chat. Feel free to email me the word sublimation to get your CEU credits at the end. I'll also be sending an email to everyone with a copy of the presentation, a recording, and then a reminder about that. So I just wanted to throw that in there. Thanks.
Okay, so we talked a little bit about this already, but aggravating factors here to cause ice dams or make them worse. Um, there's a minimum amount of ventilation required by the building code that will not prevent ice dams from occurring. Um, Another rule of thumb, you can never have too much ventilation. That is true. However, the ventilation has to be properly placed. Um, the example or the photo on the right there, you see that there's squarish vents in the lower part of the roof, and then at the top, there's a ridge vent. Now, what's going to happen in this situation is the air is going to enter down at the bottom through the soffit, but it's going to vent out through those square vents and never get to the ridge. And what will happen then is the area between the square vents and the ridge is going to be warm because you're basically not circulating any air from the square vents up to the ridge. So having a large amount of ventilation is good, but it has to be, the vents have to be placed in the proper areas. If those square vents are up much closer to the ridge, then they would be effective, but in their position, they're not. So that's important as well as having the volume of ventilation. And obviously, you can mechanically vent attic spaces. Typically, those types of fans work on both thermostats and humidistats. So in the summertime, you want an attic fan to turn on when the temperature gets, to a certain point, because you want to try to keep the attic cooler and therefore the house cooler. In the wintertime, um, the fan will never turn on if it's only on a thermostat because it's never warm enough to cause it to come on. So you need a humidistat as well. So when the humidity in the attic gets to a certain level, the fan kicks on and vents that out, and that helps prevent condensation. Um, so if you're going to be installing or contemplating installation of mechanical attic fans, make sure that they have both of those on there, humidistat and thermostat. Okay, so again, I talked earlier, not enough insulation or it's not installed properly. And there's areas, so the photo on the right shows blown-in insulation, in this case, with these are green baffles instead of pink ones, but those are ventilation baffles. They keep that blown-in insulation from covering the soffits and allow the airflow into the attic. Um, but there's other areas that sometimes aren't really thought about, which basically is areas in the attic where penetrations occur from the living space. The photo there is showing it's possibly a bathroom exhaust vent or a closed dryer vent. It's got a big chase that it comes up in, but that's wide open, and you get from that large amounts of heat loss up into the attic space. So it's important that that should be closed off and insulated to keep that from happening. Another area is the attic access hatch. In many cases, those are just a piece of gypsum board, seal it, drywall, and there's no insulation on the back. So you have this, 2 foot by 3 foot or 2 foot by 2 foot hatch cover that's not insulated. Again, large heat loss through that. Um, so, those are, and I talked earlier about recessed lights in a second floor ceiling or top floor ceiling. Yeah, those have to be, uh, you know, uh, given some consideration to making sure they don't allow a lot of loss of heat into the attic space. The other thing with recessed lights is you have to make sure that um, they are able to be contacted by insulation. Some of them have to have a clear space around them or they become a fire hazard. And there are recessed light fixtures made that will allow, they're internally insulated to prevent the heat from causing a fire, and you can push the attic insulation right up against them. But you got to make sure you have the right type. I talked about condensation earlier. Obviously, cold and warm and moisture result in condensation. In this case, it's on a glass of water. However, it's the same process in an attic. The warm, moist air, the roof deck is the cold glass. There's moisture in the warm, moist air. When it hits that cold roof deck, it condenses. And yeah, as I said earlier, if you're seeing rusted nails inside your attic, you have a condensation issue. And if it's severe enough, that actually can deteriorate the sheathing and the framing. Also, as this slide shows, if you see a line of water, evidence of water droplets on the insulation, that's also a sign of condensation. Usually what happens is the moisture condenses on the nails and it drips off the nails onto the insulation. And since the nails are in a line, then the droplets are typically in a line. Also, the sheathing underside can get discolored or even deteriorated as a result of that. Um, okay, so talked about this a little earlier as well. Um, the flashing, when the snow is above the top of the flashing, you can get behind it, so that's an issue. Now, typically, and I know that when Kipcon does roofing specs, we will take the same ice and water shield type membrane material and put a foot and a half down on the roof deck and a foot and a half up the wall and seal that joint even without the metal flashing. And then the metal flashing would go on top of that. And that ensures that, I mean, I guess if you got more than a foot and a half of snow on top of the roof deck, you might still have a problem, but that pretty much ensures you'll never have any leaks through those areas. We do the same thing in the valley. In the photo up above, the right-hand side of that, you can see that there's a valley. It's covered with snow, but it's running diagonally up probably a dormer that's coming out there that you can't really see. And we would span the valley with a piece of ice and water shield. Again, as I said earlier, they come 3 foot wide, so you have a foot and a half on either side of the valley. And that type of thing tends to minimize, even if you get ice dams and things like that, minimize any issues as a result. Okay. Yeah, here's the valley. And again, this condition, because of that diverter at the bottom, that just aggravates the condition. Okay. What do you do when you get ice dams and you're getting water penetration and the residents are calling and they're losing their minds? There's not much you can do. Um, if you could get the snow to completely melt off the roof, that would eliminate the problem. But when you have the right weather, like what's going on this week, the snow's not melting very quickly. Um, you can have people go up on the roof, as you see in that photo, and shovel the snow off. Um, Very dangerous, and that will, as I said, if you get rid of the snow, you get rid of the problem. But that's a really dangerous thing for the workers, and also tends to result in damage to the roof shingles because they're using, as you can see in the photo, snow shovels to shovel the roof off. The shingles aren't really made to be shoveled with snow shovels, so uh, you end up with damage, which um, when you're weighing the how bad the issues are with um, I'll answer that question in a second about how much snow a roof can handle. Or I'll answer it now. Uh, the roofs are designed, depending on where you're located, for a certain amount of snow load, certain amount of load on them. Um, and so every roof is somewhat different. So I can't give you an answer and say, oh, it can handle 3 feet of snow or 2 feet or 6 feet. Um, it really depends on the specific design of the building and where it's located and what amount of load it's designed for. It's designed for a certain number of pounds per square foot of weight, whether that's snow or anything else. Um, but yeah, I can't really give you a specific answer on that. Um, Getting back to shoveling, yeah, you're gonna cause almost certainly going to cause damage. Among other things, the guys shoveling the snow aren't going to care if they damage the shingles. They're trying not to fall off the roof. Um, so that is a short-term solution, but I wouldn't recommend it. And you got to shovel the whole roof off because if you only shovel or clear the roof down by the gutters, let's say you do what you can where you're standing on a ladder, the ice dam is just going to, with the proper weather conditions, the ice dam will just form higher up the roof then. Um, so wouldn't recommend shoveling. Here's another question. Have I ever seen a roof collapse because of the snow? Yes, occasionally roofs do collapse because of snow load. It's not very common, and it's generally what you see generally is flat roofs, um, where the snow is sitting on the flat roof. It's not designed for that much load. Um, but yeah, occasionally it does happen. As I talked about earlier, real quick, ice damming can still occur without the gutters. The gutters aggravate the problem, but they're not the cause of the problem. So you remove the gutters, you can still get ice dams. Again, reiterate, it's weather conditions that cause them. So gutters or no gutters doesn't make a difference. Well, a little bit of a difference, but uh, they can still occur. All right, so snowmelt devices. These can be effective, but again, you see in both of these photos, um, they are melting the snow on the lower portion of the roof. So you can still have ice dams form above that. Um, but um, you know, by depending on how far up the roof you go, um, you can then get it where the snow melt is not refreezing as quickly as it is down at the eave of the roof where the roof is very cold. Um, I would say that using this is probably something that you would use on a spot basis. If you have, say, porch roofs over building entrances, and you can extend these heat cables up and clear the entire roof, then it's probably worth it because if you got people walking into the building and there's ice on the roof and icicles and they can fall and hurt people and so on and so forth, they may work. Generally, there's some issues with them. Um, you got to make sure that they're either on some kind of timer or a thermostat or some sort of system where they can be turned on and off because you don't want them running when there's no snow on the roof. And, you know, uh, they tend to be high maintenance, after a couple of years that the cables start to not work and, but they do provide relief because they're melting the snow. But uh, the blower photo in particular, you can see there's still a huge blanket of snow right above where those cables are, and even in between the cables. So uh, they may not, be able to overcome certain weather conditions, even though they're melting snow in some areas. Um, you know, Again, go back to you try to minimize the condition and the results of the condition, and all of these things I've talked about already: insulation, ventilation, sealing up penetrations through the roof or through the ceiling, that type of thing. They can minimize your problems. Doing that can certainly eliminate a condensation problem. It will not necessarily eliminate ice dams or keep ice dams from forming, but it can minimize it. One of the things, though, is to make sure if when you re-roof your buildings, that there's ice and water shield at the eaves and these other vulnerable areas, because that really helps not to prevent the ice dams, but to prevent the damage resulting from the ice dams. One thing to consider though, there was a time probably 20, 25 years ago, we had a really bad winter with regard to ice dams. And so the next year, everybody wanted their entire roof covered with ice and water shield underlayment before the shingles went on when they were doing shingle projects. And okay, that in some cases that was done. And then the problem was that created condensation problems in the attic spaces, particularly when it was done over cathedral ceiling buildings. So you 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 want to kind of assess the situation. If you had ice dams and it was 2 or 3 or 4 feet up the roof, then two rows of ice and water shield would suffice to prevent that from occurring again. Um, but yeah, I would not encourage covering the entire roof with it. Again, you got to look at where you have leaks of heat and into the attic and eliminate those. If there's ductwork up there, you want to try to insulate it. Some buildings have the heating and cooling system in the attic space. You want to make sure all the ducting from that is insulated, things like that. Uh, Improve ventilation and insulation. I went into that earlier. Um, Ventilation, and again, you want good ventilation, but properly placed and properly designed so that it's effective. And if you have blown in or bad insulation, make sure that you keep the soffits open. Spray foam insulation is just the way it's installed. It leaves areas for ventilation. And I talked about a lot of this already. Longer term solutions, ice and water shield in vulnerable areas. Uh, Make sure that you're minimizing heat loss, proper flashing around chimneys, dormers, things like that. All of that will, again, not prevent ice dams, but prevent or minimize the damage resulting from them. Um, and I'll answer that question in a second. I just wanted to point out, I talked about the kick out flashing earlier. That's very important. And that's important even when, not even with regard to winter conditions, but all year round, because without that, the water is going to run down into the end of that gutter and it's going to run down over the side of the gutter and down that wall and potentially get behind the siding there and cause damage to the wall behind it. Uh, Chelsea, the question was about,
Is metal flashing, sorry, is metal flashing not used in valleys?
yeah. Um, there's different types of valley construction. There's open valleys which use a big piece of metal flashing, um, and then the shingles are woven into that. There's a woven valley where the shingles are actually woven together uh, to create the weather tightness there. And then there's what are called closed cut valleys, which are partially woven, and then the shingles are cut in a straight line down, down the valley line. Um, and that's an easier way to install it than weaving the shingles. That's a little more complicated. Uh, Open valleys are not used that much anymore. They're more vulnerable to water penetration. A woven valley is the best one. And, that would be what I would recommend if you're going to install a new roof. And that's pretty much it. Anybody has any questions, I'll be happy to answer them.
Yeah, I know we went a little over time, so thank you all for
Sorry
sticking with
about
us.
that.
No, that's not. it was beginning with a little complication, so I apologize to everyone. But if you have any other questions, you can throw them in right now. We'll stick around for a couple more minutes, or you can shoot us an email with the questions. And then I'm going to be sending an email, like I said earlier, to everyone with a copy of the presentation. So you'll have a copy of this along with the recording. And then if you want to reply to that with any, like I said, questions or for your CEUs, again, the keyword was sublimation. So feel free to reach out to us, and we really appreciate everybody being here. Hopefully this was helpful again with everything going on, and we appreciate your time. So thank you so much, and thank you, John. Great job.
Thanks, everybody.